Next, let's look at average precision score. So precision again is given by this relation, which is true positive divided by true positive plus false positive, and then recall is given by true positive divided by true positive plus false negative. And this is similar to what we have seen earlier. So let's go back a few slides, and here we can see, so the true positive rate is true positive divided by true positive plus false negative, and here we have true positive plus true positive divided by false negative, which is the recall. Now the average precision is then calculated as by that formula, and here is the implementation of that. We specify the y true, and then we specify the y scores, and then we get a value which is 0.833 for a single label. And if there is multi-label case, that is if you have more than one target y columns, then we have similar output shown here. And this is just a manual calculation of the same relation that we saw earlier. If this is the data set, and if we get the precision recall curve, we get these values out for precision recall and thresholds. Now if we arrange the values for recall and precision as shown here, so this would be the recall that is listed here, this is the precision listed here, and if we use the formula, so 0.5 minus 0 multiplied by 1 plus 0.5 minus 0.5 multiplied by zero point 0.5, and then 1 minus zero point 0.5 multiplied by 0.67, and that again gives a value close to 0.83. Next is Brier score loss. Now with loss, the idea is for the score is switched. The lower the loss, the better it is. That is to say, the the values are, or the predicted values are closer to the true values. And the Brier score here measures the mean square difference between the predicted probability and the actual outcome. And here is the implementation of that. We have the y true values, and these are the categorical. Then we have the y probability. So when you input y true and y probabilities, we get the Brier score loss. And then there are other optional arguments that we can also pass to the Brier score loss function. And again, the value of 0 is best, 1 is the worst. Next, there is another metric called F1 score, F1 underscore score. So this is a weighted average of precision and recall given as shown here. And this particular method takes in arguments shown here: binary, micro, macro, weighted, and sample. So binary is for binary class. Micro is matrix calculate matrix globally by counting the true total true positives, false negatives, and false positives. And then for macro, it takes into account the imbalance in the data set. Weighted uses calculates the average weight weighted by support and also accounts for imbalance. Then samples, it calculates the matrix for each instance and then finds their average. So to get a good grip on what these do, I'd suggest running different codes and seeing it how that works. So for example, here we have these two values, y true and y pred. If we specify macro, we get a value of 0.5. We specify micro, we have value of 0.7. For weighted, it's 0.6. If it's none, then we get these values. And for multi-label, this is also can be used for multi-label classification, where we get the values of F1 score shown below. Again, here 0 is here again we are switching how it is interpreted. Value of 1 is the best, and then 0 is not a good value. Next, we have value for log loss, and it is can the string that can be used is called negative underscore log underscore loss, and here we have negative log likelihood of logistic model. So that is given by this relation is negative of y log p plus 1 minus y into log of 1 minus p, and p is the probability, y are the labels 0 and 1 in this case. And whenever we are looking at loss, the lower the loss the better it is, so 0 is better. But now if we look at negated value of that loss, then of course value closer to 0 would be the best value, and then negative, the more negative the value is, the worse the model fit is. And here is the implementation of log loss. We have these two values, y true and y pred. So y pred is showing the probability of an probability for it to be an apple and not an apple, and again same case for all of these. And so here we have value of 0, and here we have value of 34, and here we have value of uh, 0.1. So the value here is 34, and as you can see, the higher the value, the worse it is. Now moving on, there is something called precision score. The precision underscore score, the relation is the same as we saw earlier, true positive divided by total predicted positives, and uh, the implementation is standard as we saw earlier. Again, this has the arguments that can be used macro, micro, weighted, and none, and also can be used for multi-level classification. Similar to the precision score, we also have a recall score that is shown here, which is true positives divided by total actual positives. And here what we had was total predicted positive. So the implementation again is similar that we saw earlier. So recall underscore score is what we need to import from the Scikit-learn dot metrics. Now a new metric here, as we can see, is the jaccard score. So jaccard score is the ratio of these. So if you have seen these diagrams before, let's say we have a set A here in blue, set B in green, and the overlap region shown here is in orange. So that's the value that goes in the numerator, and the total value, that's the union, goes in the denominator. The implementation of jaccard score is similar as we saw before. Jaccard underscore score, and we can specify the values for y true, y pred, and then we can specify this argument for average. Next, let's look at what is ROC underscore AUC underscore score. So the ROC stands for receiver operating characteristics curve, and AUC stands for area under the curve. The receiver operator curve shown down below here shows the graph where we have the false positive rate on the x-axis and the true positive rate on the y-axis, and those are shown here. So basically false positive rate is how many false positives are there, and then true positive rate is how many true positives are there. And in this plot there is a diagonal dotted line that tells that lines closer to that line uh, tells that the models are not good at separating the classes, and the farther you go away from this line towards this line shown here by the magenta color, the model are good at separating the data points. So a value of 1 is considered as good, and the lower values are considered as not good. And here is an implementation of the ROC underscore AUC underscore score. We have y true, and then we have the y paired probabilities. Based on that, we can get the score values that are shown here. And it can also be used for multi-label classification that is shown down below.